Okay, so we've got multiplying and dividing of decimals, and this is going to mostly finish up our discussion of fractions and decimals for our first unit. Alright, so here is the standard algorithm for multiplying decimals. First of all, you set up the problem vertically as if you're just multiplying whole numbers, and then after the answer is achieved, you move the decimal point over the sum of the number of places in both factors. So let's take a look at one. We have 7 1400ths times 9 6/10. So essentially you line them up the way you normally would. Do your multiplication by both numbers in the place value, and then you get an answer, a whole number answer, in this case 68,544. But then what you need to do is you count up the decimal points, 1, 2, 3, so that would be 3 decimal places, and you apply it to the answer. So moving the decimal point from a whole number to essentially what you're doing is dividing by 1,000, and now you end up with 68.544. So in this case, 7 1400ths times 9 6/10 is 68 544 thousandths, which would make sense if you were to round this or estimate it. 7 times 9 is 63, and you have 68. So that would be a reasonable answer. All right, so how does this come about, the algorithm for multiplying decimals? Well, here's the proof. We take our 7 1400ths, and that is the same as 714 over 100, which if we're using exponents, you can write as 714 over 10 to the second. Remember that this is a definition of a decimal. A decimal is a decimal fraction, and so therefore can be written as this fraction. So if you apply the same type of reasoning to 9 6/10, you get 96/10, which is 96 over 10 to the first power. So we set this up like a multiplication problem, and by our product formula theorem, we have 714 times 96, and then we have our 10 to the second times 10 to the first power. Well, essentially what this means is 10 times 10 times 10, and we are going to dabble a little bit in the laws of exponents. When you have an exponent times an exponent, basically what you can do, especially, well, only when the bases are the same, is you can just add the exponents. So notice how 2 and 1 becomes 2 plus 1, because you have 3 tens. So in this case, 714 times 96 is 10 to the third power. And if you were to multiply that out, you get 68,544 over 1,000. Well, notice the 3 here. The 3 coincides with how many times we move the decimal point up here in the algorithm. So essentially what we have is the whole number over 1,000, and when we move the decimal point from right to left, you are essentially dividing by 1,000. So that is where 68,544 thousandths becomes 68 544 thousandths. And you can put an or, because either one of these answers is correct. So that's why I changed the equal sign to an or, because it's the same thing. All right, go ahead and try this problem by solving it using the fractions instead of just a standard algorithm, and then continue the video to see the answer. Okay, so here is the proof that you should have. By converting the decimal back to a fraction using definition of decimal, we have 30,504 over 10,000, and 1 800ths becomes 108 hundredths. Then by setting this up as a multiplication problem, We use PFT, our product formula theorem, to put them together. And remember, 10 to the 4th power times 10 to the 2nd power is essentially 6 tens, which means we can just add those exponents, 4 plus 2, and get 6. So 30,504 times 108 over 10 to the 6th power gives you 3,294,432 over a million. So you can leave it like that, or you can actually write it as a decimal, and this is where you get 3 and 294,432 millionths. Okay, so that's what your answer should be. Again, either you could leave it either in this format, or you can leave it in this format. All right, so let's talk about dividing decimals. Here is an explanation of the standard algorithm. Set up the problem using long division. Make the divisor a whole number if it is not, by moving the decimal point. However many times you move the decimal point in the divisor, you need to do the same in the dividend. Raise the decimal point to in the dividend up to the quotient and solve. So here's an example. 2 and 498 10,000ths divided by 14 and 3/10. So we set this up as a long division problem. 2 and 498 10,000ths divided by 14 and 3/10. So what ends up happening here is we have the decimal point in the divisor, which is not making this a whole number. So we're going to need to multiply this by 10, which means we also multiply this by 10, and we move the decimal point over one place. Now we end up with 143 into 20 and 498 thousandths. Then this decimal point, we need to remember to float it up to the top so that it is in our quotient. And then you go ahead and solve long division wise, and you should end up with 0.1433, and it goes on for a little bit more beyond that. But it is it's either a repeating decimal or a finite decimal. All right, so how does this work with fractions? Well, again, we need to convert our decimal back into a fraction state. So 20,498 over 10,000 is 10 to the 4th power. And for 14 and 3/10, we have 143 over 10. So now we have our complex fraction. Whenever we do division of fractions, we have a complex fraction, which by using our definition of division of fractions, we end up multiplying by the reciprocal. So notice how 143 over 10 to the 1st power becomes 10 to the 1st power over 143, and we are multiplying. So using our product formula theorem, we multiply across the numerators and multiply the denominators. Now you can also see that we're going to have an issue of cancellation, and when we do, if you notice, I've put this in exponent form. If I have 10 to the 4th power here and I'm going to cancel this out, then basically what I'm doing is I'm subtracting 1 from the exponent. So this now becomes, through the cancellation law, 20,498 over 143 times 1,000. So notice how 4 minus 1 becomes 3, 1,000. So here's our 4 zeros minus a 0 because we're going to cancel these out, and it's going to leave us with 1,000 here. And so here's our answer. In essence, this is the answer to the division problem. 20,498, 143 thousandths. But of course, if you were to divide that, you would get, as a decimal, it would turn into 0.1433, which is exactly up here. Let me go back to this part right here. So this would be 143 Notice how that corresponds with 143 here. And if we move the decimal point 3 times like it's saying, then that's where you get the 20.498. So here's our algorithm, why we can do this. Essentially, we are dividing each number by 1,000 so that the 143 can go into now 20.498. So that's where this correspondence or relationship comes in. But it doesn't matter, even if I were to take this whole number and divide it by 143,000, you would still end up with the same answer. All right, so let's go ahead and try that. And again, this is OR. So this answer is OR. It doesn't matter which one you use in your quiz. All right, so here's a problem to try on your own. And again, you can use your calculator to do the actual division part of it, or you can do it longhand. Go ahead and try this, and then restart the video so you can see the answer. All right, so here's our proof. If you take 201 4/10, that becomes 2014 over 10. And 3 600 becomes 306 over 100. If you set that up as a complex fraction so that they are being divided, then by definition, division of fractions, we end up multiplying by the reciprocal. 306 over 10 is the same as 10, or not the same, but the reciprocal of 10 squared over 306. By using our product formula theorem, we multiply across. And you can see we're setting up for another cancellation. So that becomes, the 10 goes away, and this becomes 10, and 10 times 2014 is 20,140, and 306 times 1 is obviously 306. So here is our answer. If you want an exact form, this is the answer, 20,140, 306th. But if you were to turn that back into a decimal, it would be 65 and 81 plus some other numbers after that. So this is how the definition, or this is how the algorithm for division of decimals came about. Is basically, in this case, you would end up with a whole number here, but you would be dividing that 20,140 by 306, which if you set this up using the standard algorithm, you would end up with the same thing. All right, we'll practice these more in class.